Hello everyone, welcome to the course on Open Source CAE. Today, we are going to introduce PrePoMax, a graphical pre- and post-processor for CalculiX FE Solver. In this introductory course, we are going to discuss about what is PrePoMax, what are its capabilities, where and how to get it, how to install and run, and we will see some examples on how to simulate with PrePoMax. So, let's get started. First, let's see what is PrePoMax. PrePoMax is an open source pre- and post-processor for CalculiX FE Solver. CalculiX is a free three-dimensional structural finite element program or solver. For more information on CalculiX Solver, follow the link in the description. PrePoMax has a flexible graphical user interface to prepare FE model, set up the analysis, and post-process the results efficiently. The interface, setting up the problem, and post-processing are similar to abaqus FE Solver. Most of the options are also similar to abaqus. So let's exploit the power of CalculiX FE Solver using modern graphical user interface with PrePoMax. The three basic steps of any finite element analysis are preprocessing, solving, and post-processing the results. PrePoMax deals with the pre- and post-processing part of the simulation, while the solver part will be taken care by CalculiX. Now, let's discuss the capabilities of PrePoMax. PrePoMax has the pre- and post-processing capabilities right from the CAD import to visualizing and plotting the results. We are going to discuss all these capabilities in this course. PrePoMax can import 2D and 3D geometry, FE mesh, and also input files from the other FE softwares. The supported CAD formats are STEP, IGS, BREP, and STL. The CAD support for PrePoMax is based on the open source Open Cascade platform. The FE mesh can be imported from Universal, NetGen, Gmesh, and MMG mesh files. PrePoMax can import the input files from abaqus and CalculiX also. In addition to import, PrePoMax can export CAD model after preparing for analysis, deformed model from analysis in STL format, FE mesh, input files, and deformed mesh to CalculiX and abaqus. As discussed earlier, PrePoMax supports 2D and 3D geometry input from various formats, and we can perform few basic operations on the geometry to prepare it for meshing or for analysis. The imported geometry can be scaled to the required size using the scaling transformation. When performing the analysis of surface bodies, if normals are misoriented in CAD, they can be flipped after importing. We can split the faces of geometry using points from the model vertices. This is useful for applying loads and boundary conditions, creating contacts, and refining mesh at split surface. Multiple parts which are sharing a common surface can be combined as a single part. This is useful to have a continuous mesh and to avoid contacts. The geometry can be analyzed to find the features like edges and faces within the tolerance specified. This is useful for finding the smallest features in the model and to decide the minimum element size. Also, based on the information on feature size and location, these features can be retained or removed. Now, let's see the meshing capabilities of PrePoMax. PrePoMax has a very powerful geometry-based mesh generation algorithm with which we can mesh or discretize the CAD model most efficiently. Here, mesh is performed by an open source NetGen library. For more information, visit ngsolve.org. At present, PrePoMax can generate both linear and parabolic elements. The element types which we can generate using PrePoMax are 3D solid tetrahedral elements, 3D shell trias and quads, and 2D plane trias and quads. Though PrePoMax cannot generate hexahedral elements, it can import hexahedral and wedge elements from other mesh generation algorithms. As already discussed, PrePoMax can support both linear and parabolic elements, that is, elements with mid-side nodes. The naming convention for different elements which PrePoMax follows are 2D plane stress elements are prefixed with CPS followed by the number of nodes in that element. Similarly, plane strain elements are prefixed with CPE and axisymmetric elements are prefixed with CAX. 3D shell elements are prefixed with S followed by number of nodes. 3D solid tetra and hexa elements are prefixed with C3D followed by number of nodes. Now, let's discuss the mesh refinement capabilities. To refine mesh locally, modal vertices, edges, faces, and parts can be used. In the first example, the point on the ball and the cube where they are touching are refined with modal vertex to capture the contact stresses. Similarly, in the second example, the mesh is refined at the line contact between rail and wheel with modal edge. In the third example, both edges and faces are used to refine the mesh. In the flange joint assembly, bolts are selected for mesh refinement, that is, parts of an assembly is used for refinement. Now, let's see what are mesh and geometry based definitions. We can generate geometry and mesh based definitions called sets or components or named selections. These definitions are used to apply different section properties, materials, loads, boundary conditions, and connections. In simple words, sets are useful to handle model entities or parts of the model. In this example, a node set called loading_face is created and later used for applying the load at that location. Here, two element sets, set 1 and set 2, are created and used to apply different materials for different sets. Here, surface sets for washer, bolt holes, and wall face are created and later used for applying the boundary conditions. Now, let's see what is a reference point and how to create it in PrePoMax. Reference points are geometric points created within the CAE environment. These are useful for creating points where vertex is not present in the CAD model. In PrePoMax, we can create reference points by coordinate input or with model data. In this example, we have created 3 remote points at the center of each hole. These 3 remote points are later used to create rigid connections, applying loads and boundary conditions. Now, let's discuss how to create and apply materials. PrePoMax has a built-in material library containing few elastic materials such as steels, plastics, and aluminum alloys. We can also create and add user-defined materials to the library. PrePoMax currently supports linear elastic and plasticity material models with isotropic, kinematic, and combined hardening rules. Next comes sections. With sections, we can assign different sectional properties and materials for different parts or element sets of the model. In this example, different sections are created for flanges, webs, and stiffeners for assigning different shell thicknesses. Next, we will see what is interaction. There are two types of interactions between different bodies are possible in PrePoMax. They are constraints and contacts. PrePoMax has 3 different constraints, namely point and surface springs, rigid body, and tie constraint. Spring constraints are used to provide discrete elastic supports with reference to a node, element, reference point, or a surface. Rigid body constraints are used to apply remote loads or offset loads and boundary conditions. To create a rigid body constraint, it requires a reference point. Tie constraints are used to connect two parts rigidly like a bonded or welded joint. They are generally used to connect two dissimilar meshes without contacts. In this example, two rigid constraints are generated from a remote point to the adjacent mesh at the hole. The loads and boundary conditions applied at the remote points are transferred to the body using rigid constraints. In the second example, two numbers of point springs are generated at nodes and a surface spring is created with reference to washer surface. These springs with finite stiffness provide supports to the bracket. In the third example, the tie constraint is created between master and slave regions of the brackets. Both load and deformations of the top bracket are transferred to the bottom one through the tie constraint. The other way of modeling the interaction between two bodies is by creating the contact and target elements between them. The surfaces that touch each other to transfer the forces without penetration are said to be in contact. Contact is a changing status nonlinearity. PrePoMax has three interaction models. Surface behavior is used to define the contact pressure over closure relationship. Friction model is used to define friction and stick slope between master and slave. Gap conductance is used to define conductive heat transfer between contacting surfaces. PrePoMax can search the contact pairs based on the search criteria like distance, angle, etc. In this example, the default search criteria for distance is 0.01. Angle is 35 degree. Type is contact. Surface interaction type, which we created earlier, can be used here, and method is surface to surface. With these search conditions, all possible contact pairs are populated in the table. If required, for each of the contact pair, properties can be changed through the right side data panel. Amplitude allows us to vary the magnitudes of load, displacement, and other variables with respect to time or frequency within the step. In this example, the surface traction is applied and removed within 0.1 second to find out the dynamic response of the cantilever. Next, we will discuss analysis steps. PrePoMax can set up various analysis types right from basic linear static analysis to coupled thermomechanical analysis. Currently, it supports static step with linear static, contact, large deformation and plasticity, slip wear step to model the material damage due to slip friction, frequency step to find the natural frequencies and mode shapes, buckling step to find out the critical buckling loads and mode shapes of the structure, heat transfer step to carry out the steady state and unsteady state heat transfer analysis, uncoupled temperature displacement step in which a thermal analysis is performed first, then the resulting temperature field is used as a boundary condition for subsequent mechanical analysis within the same increment. Coupled temperature displacement step to solve simultaneously for displacement and temperature field. A coupled analysis is used when the thermal and mechanical solutions affect each other strongly. In version 1.4 onwards, model dynamic step, steady state dynamic step, and dynamic step are added. After completing the setup, we have to create an analysis run. Here, we created analysis 1 as the name of the run. PrePoMax supports multi-threading of the solution. From the settings, under CalculiX, we can set number of processes for the solutions. Here, we can also change the working directory, executable file location, and default solver. Now, by right-clicking on the analysis one, we can run the analysis. Like all other FE softwares, here also we can monitor the solution output, status of the run, and convergence. Kill option is used to stop the solution at any time. After finishing the run, by clicking on the results button, PrePoMax takes us to the post-processing. Now, let us discuss the post-processing capabilities of PrePoMax. PrePoMax has a very flexible post-processing interface which allows us to visualize field and history outputs with ease. Field outputs are 3D scalar fields or contour plots. Like other CAE tools, PrePoMax can create contour plots for displacement, stress, strain, temperature, heat flow, etc. For structural analysis, by default it creates displacement, stress, and other field outputs. Additional fields can be added in this step before running the analysis. PrePoMax can generate field outputs for node, element, and contacts. In each category, various variables are supported to generate contour plots. Like any other FE software, PrePoMax can plot different kinds of deformed shapes. We can query or probe the results. We can show the geometry in the results, and sectional view of the contour plot is also possible. History outputs allow you to read and plot the results at a specific location of the model or at the remote points. History outputs are available for node, element, and contact types. In each type mentioned earlier, we can select nodes, surfaces, edges, vertices, and parts to get history outputs. In this example, there are two history outputs created for displacement as well as force reaction at boundary condition. The history output for displacement of the node at the extreme end of the bracket is shown here. We can get the list of displacements of the node with respect to time or load increments. With this data, we can plot the 2D graph for displacement versus time or increment. Similarly, the history output for force reaction at the washer area is listed and plotted with respect to time or increment. From the history output, the data can be exported to Excel or similar programs to compare and generate plots between different variables. PrePoMax can generate history outputs for node, element, and contacts. In each category, various variables are supported to list and plot 2D graphs. Now, let's see what are the transformations in post-processing. When we carry out analysis with symmetry boundary conditions, it is possible to show the expanded contour plots using transformations like symmetry expansion, linear, and polar array. In this example, we used a quarter symmetry model and carried out the analysis. Then, the results on the quarter model are expanded using symmetry transformations in X and Z directions, which are the normal planes of the symmetry. So far, we have discussed the pre and post processing capabilities of PrePoMax. Now, let us see where to get it. Open Google and search for PrePoMax, or follow the link in the description. This will take us to the home page of PrePoMax website. Here, we can see what is PrePoMax, what are its capabilities, etc. Now, by clicking on the downloads, go to the download page. Here, we can see what are the prerequisites to run or install PrePoMax, installation procedure, and under downloads, different versions of PrePoMax. The present version of PrePoMax is 1.4. Now click on the link and download PrePoMax. This will download PrePoMax software in zip format. Now right click on the downloaded zip file and extract. If you open the unzipped folder, we can see PrePoMax executable along with various subfolders containing libraries, sample models, NetGen measure files, CalculiX solver files, temporary folder and material library. Now right click on the PrePoMax executable and run as administrator, or simply double click to open PrePoMax. No installation required. Now let's create a new model and import a geometry from sample models. So this is how we can download and run PrePoMax. Now let's simulate in PrePoMax with an example. Open PrePoMax, create a new model, select 3D under model space. Under unit system, select mm, turns, second, degree centigrade. Now let's import the model. It's a cantilever beam. Now right click on the meshing parameter and click on create. Select the geometry and set the minimum element size as 5 mm. Now in main menu, go to mesh and click on create mesh. This will generate the mesh. Now under FE model tree, right click on the material and select S35 and add material. Right click on the sections and click on create. And select the geometry. Set the material as S235, which was selected in the previous step. Now right click on the step and create. Here select the static step as analysis type. Right click on the boundary conditions and create. Here select fixed and apply on cylindrical surface of all holes. Now right click on the loads and create. Here select surface traction and apply on the surface at the free end of the cantilever. Set the magnitude of force as 1000 newtons in negative y direction. Now Right click on Analysis 1 and run the simulation. This will open the simulation monitoring window with output, status and convergence. Kill is used to stop the solution. So this will take a while to solve, and finally job is finished. Now if you click on the results button, it will take us to the post-processing. So we can see that this is showing a displacement plot. So let's display the displacement in y direction. Now click on the mices under stress to display one mices stress plot. So this is how we can simulate in PrePoMax. This concludes the introduction to PrePoMax, and we are planning more videos in this series. Thank you for watching and keep learning.